In this video we will be looking at square matrices. A square matrix contains the same number of rows and columns. The order of any square matrix can be written as m times m. Examples include the following three matrices. The first matrix is a 1 times 1 square matrix, the second one is a 2 by 2 square matrix, the third one is a 3 by 3 square matrix. Important notes for square matrices. Only square matrices can be squared, that is, multiplied by themselves, and only square matrices have a multiplicative inverse, which we represent as a to the power of -1. The identity matrix is a square matrix whose entries in the leading diagonal are all 1. All other elements are 0. So here are examples of the identity matrix, and you can see that the leading diagonal runs from the top left to the bottom right of the matrix, and all those entries are all 1. And all the other entries are 0. For the identity matrix and another matrix A, where multiplication is defined, we observe that A times the identity just gives the matrix A, and similarly the identity matrix times A gives A. In the real number system, the identity is multiplying by the number 1. For matrices, we multiply by the identity matrix to maintain the same value. The multiplicative inverse of A is denoted by A -1, and it's important to note that this is not 1 divided by A, but just a convention to represent the inverse. The multiplicative inverse is defined to be the matrix such that A multiplied by its inverse is equal to the identity matrix, and similarly, the inverse matrix of A multiplied by A also gives the identity. For a matrix that is A, B, C, D, so a 2 by 2 square matrix, the multiplicative inverse is given by 1 divided by AD minus BC, and then we swap the values of A and D and multiply B and C by -1, and that will give us the multiplicative inverse of A. The quantity AD minus BC, which appears down here, is known as the determinant, and we can represent that using det A. Det A is just a number, and it's important to note that if that number is 0, then the inverse does not exist for the matrix A. For this example, we're going to consider the matrix A, and we need to remember that this position here is A, this is B, this is C, and this is the position of D. So the first thing we want to do is calculate the determinant of A, and we know that the determinant of a matrix A is given by A times D minus B times C. So for the matrix in this question, we have A is 5 and D is 3, and then we subtract away B is 2 and C is -7. So evaluating that, we have 15 plus 14, which equals 29. So as this is a non-zero value for the determinant, we know that the inverse can be calculated, which is what we will do in part B. So for part B, we know that the inverse, A -1, is equal to 1 divided by the determinant of A. And then we have A and D have swapped positions, and B and C are multiplied by -1. So for our matrix in this question, we have A inverse is equal to 1 divided by the determinant of A, which is 29, which we found in part A. And then we have A and D swapping positions, so we have 3 here and 5 here, and then B and C are both multiplied by -1, so where it was 2 it's now -2, and where it was -7 it's now +7. So this here is the inverse of our matrix A. Next we're going to consider the matrix B, which is shown, and for part A we want to calculate the determinant of B. So once again we can label all of these entries as A, B, C and D, and we can use that to calculate the determinant. So we know that the determinant of a matrix is equal to A times D minus B times C. So for our matrix, A is -4 and D is 8, minus B, which is 0, times C, which is 3. So this just equals -32 subtract 0, so the determinant is -32. And because that is a non-zero value for the determinant, it means it's possible to calculate the inverse for this matrix B. So the inverse of B, which is represented as B -1, is equal to 1 divided by the determinant, which is -32, and then we swap our values of A and D, so we have 8 here and minus 4 here, and now we multiply B and C by -1, so 0 times -1 is still 0, and 3 times -1 is -3. So that is the inverse of our matrix for this question. In the next example, we're going to consider the matrix C as shown, and the first thing we can do is label the entries as A, B, C, and D. And now for part A, we want to calculate the determinant of C. So we know that the determinant of a matrix is going to be equal to AD minus BC. So for this matrix C, we have A is 3 times D is 4, minus B, which is 1, times C, which is 12. If you evaluate that, you have 12 subtract 12, which equals 0. So because the determinant is 0, it is not possible to calculate the inverse C -1. So after this video, you should be able to understand that a square matrix has the same number of rows and columns. You should be able to write the identity matrix of order m times m. You should be able to calculate the determinant of a 2 by 2 square matrix. And finally, you should be able to calculate the inverse of a 2 by 2 square matrix, that is, providing the determinant of the matrix does not equal 0.